Rudolf Zeidler. He will speak about metric inequalities under lower scalar curvature bounds. And this is the topic that his ERC grant that he recently won and is using in Münster is dealing with. Okay.
Yeah, thanks a lot for the introduction. Thanks a lot for having me speak here. Yes, so this will be about talk about lower curvature bounds, specifically lower scalar curvature bounds. But let's start slowly. A little bit about curvature. So what is curvature? I guess you might have these pictures in mind if we think about curvature, so in terms of different kinds of surfaces. But when we want to speak about scalar curvature, we need to get to higher dimensions. And their curvature is a little bit more complicated because it's not just a single numerical quantity that, in a sense, determines the local geometry. It's, in a sense, lots of different numerical quantities. And this comes about because let's say if we're in a setting of Riemannian geometry, we can define the sectional curvatures. And so they're associated to a tangential two-plane. So you get a two-dimensional subspace tangential to your manifold, and you associate a numerical quantity to that, and that's the sectional curvature. And it has a definition in Riemannian geometry, which is in terms of the metric and its first and second derivatives. However, I will not give you that definition. Instead, the way you can think about this is that you look in your space and you use geodesic normal coordinates, and you develop your tangential two planes in that coordinates. And then you essentially get a surface, and the usual curvature notion that you're used to from surface geometry is what you get. So if you apply that curvature notion to that surface, this gives you the sectional curvature at that point in that tangential two direction. And this talk will be about trying to use these local quantities to get some sort of global consequences, and specifically global consequences in terms of distance estimates. And this is actually a classical story in Riemannian geometry, and I'll recall one very classical result in this direction, which is the comparison theorem of topological. And I'm just stating here one particular case of this, and that will be the kind of situation that will be most relevant for me, namely a lower bound of the curvature by a positive constant. And let's normalize it to 1. So in that case, Toponogov's theorem tells us that, in a sense, certain kinds of distances are small if we are in a highly curved space. And specifically, what you're doing is you look at a so-called hinge in your space, which has a lower bound of the sectional curvature of 1. And the hinge is just two geodesic segments which are at a particular angle alpha, and you have particular distances from this point to this point, and another particular distance from this point to this point. And then what you do is you look at a comparison situation in the standard space of curvature 1, and that is the standard sphere, and you draw a hinge like this, which has the property that this distance is the same as this distance is the same as this distance here, and the angle is also the same. And then what you're interested in is how does the distance between the endpoints, the tips of this hinge, compare? And the statement is simply that this distance here is going to be smaller if the curvature is large than the distance in the comparison hinge in the sphere. And roughly speaking, the way, this is proved is the curvature somehow gives you control on the Hessian of certain distance functions, and then it boils down to comparing certain ODEs along geodesics. Now, this is sort of the strongest curvature notion that you could imagine, in a sense, the sectional curvature. And I eventually want to come to the scalar curvature, which is much weaker, but there will be one step in between, and that's the Ricci curvature. But before I'm doing that, I want to also consider a different kind of situation. So here we are in a situation of a positive definite lower bound by a positive constant, you could also consider the situation where you have a positive sectional curvature, but not necessarily positively bounded by a lower by a constant. It could, for instance, be a non-compact space where the curvature tends to 0 at infinity. And one can still say something in that situation. And that's another theorem that I want to mention, which is quite classical, which is stating that if we are in a complete non-compact manifold with positive sectional curvature, then M is already diffeomorphic to the Euclidean space, but not isometric, not necessarily. So this is a theorem due to Gromov and Meyer, and it's a precursor to the so-called Soul theorem. And you might actually ask, well, is it even possible to have non-compact and positive sectional curvature? Because positive curvature would you kind of think it would make everything compact, but of course you can write down easy examples where the curvature is positive, but it decays to 0 at infinity. And the standard example of this would be a paraboloid like this. It is positively curved, but it's non-compact, but it is topologically just R2. Now, let's come to weaker control on the curvature, namely Ricci curvature. What happens here is, as I said, sectional curvature is a curvature quantity associated to each tangential two-plane. And you can simplify that by picking one direction and then averaging over all the curvatures that you get in two planes that contain that line. So that in a sense simplifies the situation a bit, because you average a lot. And that gives you then one number for each unit vector if you want. And it turns out that this is still good enough to get certain distance estimates. This is the classical theorem due to Myers, or if we're going back to the surface situation, the Bonnet-Myers theorem, which tells you that if you have a lower bound of the Ricci curvature by a certain constant, and here the constant is n-1, where n is the dimension of the manifold. Now this is precisely the Ricci curvature of the standard sphere. And then again, this is sort of a comparison to the sphere in a sense that the theorem then tells you that the diameter of the manifold is bounded above by pi, by the diameter of the sphere. And here, in a sense, the proof is kind of similar. It's the Ricci curvature doesn't tell you necessarily something directly about the Hessian of distance functions, but it tells you something about Laplacians of the distance functions. And that's still good enough to get this diameter estimate. And in fact, we know a rigidity result, namely if the diameter is equal to pi. So if we're equal to the diameter of the sphere, then under these hypotheses, the manifold is already isometric to the standard sphere. So that's kind of a strong comparison to the sphere. And as in the case of sectional curvature, I want to come to sort of an analogous question on non-compact manifolds. Here, the situation is a little bit more complicated. So the first thing that you might notice is if you look at this paraboloid example from before and you cross it with something else with positive Ricci curvature, let's say take the 2-sphere, then this will have still positive Ricci curvature, but it gives you a complete non-compact manifold, which in that case will be like diffeomorphic to R2 cross the 2-sphere, which is not R4, of course. So you don't have this like completely strong restriction on the topology anymore. But you can still say a lot of things. I'll just mention one particular thing, which is a corollary of the so-called Gromov splitting theorem, which tells you that if you have a complete non-compact manifold with positive Ricci curvature, then the manifold is connected at infinity. And connected at infinity means basically that this picture here is not allowed. So you're not allowed to have more than one end. So this in particular tells you that certain manifolds, let's say if they have two ends or more than one end, they cannot support a positive Ricci curvature metric which is complete. Okay, now finally let's come to the actual topic, namely the scalar curvature. So here you kind of continue the procedure of averaging. So now you not only average over all the planes which belong to a particular unit vector, or which contain a particular unit vector, you actually average over all sectional curvatures. This is what's written here in these formulas. And then you just get a numerical quantity. And this gives you just a function on your manifold. And in a sense, the question that I want to address is, well, can you do some sort of distance estimates if you have a bound on the scalar curvature, or can you say something about the structure of non-compact manifolds with a positive lower scalar curvature bound? And here, the first immediate answer is no, because you can do some simple constructions. So the scalar curvature behaves very nicely with respect to products in the following sense, that if you just take a product, and here I mean it's just really the Riemannian product metric, and you compute the scalar curvature at a point x comma y on your product, then this is really just the scalar curvature of the one manifold at the point x plus the scalar curvature of the other manifold at the point y. And this in particular means that you have lots of flexibility to make this term positive, because you can basically take anything completely arbitrarily here, as long as it is bounded in absolute value. You can just stick something else on the other side, which is very, very positively curved, let's say a very tiny sphere, then the sum will still be positive. And this in particular means that you can construct lots of examples of manifolds with a positive lower bound of the scalar curvature with sort of completely arbitrary topology in a certain sense. But, well, not completely arbitrary, but a lot more is possible than in the case of, let's say, positive sectional or Ricci curvature. And in particular, what you notice is that you can construct a compact manifold of arbitrary large diameter with a positive lower scalar curvature bound. So the standard example would be just take the sphere, starting here in dimension 2, so n should be at least 3, and you take the product with a large circle. Has large diameter and has a positive lower scalar curvature bound. And similarly, you can do instead the sphere across the real line, and then you get a complete non-compact manifold with a positive lower scalar curvature bound, and it has two ends, obviously. Yeah? So these kind of obvious restrictions they don't apply anymore. But nevertheless, this will be the question to be addressed. And of course, we have to put now some additional conditions to get some sort of results like before. And to formulate this, I will actually have to answer a different question, a more classical question first, and that is about the existence of positive scalar curvature metrics on compact manifolds. Yeah? So this will be sort of the brief introduction to that question, which also has a long history. So does a given compact manifold admit a metric of positive scalar curvature? So the first answer in dimension 2, here it's again classical. You can use the Gauss-Bonnet theorem, which tells you that if you integrate the scalar curvature, which in that case is the same as 2 times the Gaussian curvature, is a certain topological quantity, namely 4 pi times the Euler characteristic. And that already tells you something, because you know if the scalar curvature is positive, then the Euler characteristic has to be positive as well. And this rules out all orientable surfaces except the sphere. So from this you already know that the only orientable surface which admits positive scalar curvature is the sphere. But as I said, in higher dimension situation is much more flexible, essentially because of these product constructions that I already showed you. And this also tells you that if you take any compact manifold, you take a product with the 2 sphere, you will get positive scalar curvature on that manifold. And it means you can get lots of examples here. But nevertheless, it's not completely infinitely flexible, so there are some restrictions. So even in high dimensions, there turn out to be examples of manifolds which do not support positive scalar curvature. And the first prototypical examples that were found are the so-called K3 surface and the torus. And actually the first example we found is really the K3 surface, or manifolds like that, which I'll mention in a second what the precise property it is. So this goes actually back to the 1960s. Lignerich used the spin-Dirac operator together with index theory to show that this manifold does not support positive scalar curvature. And a little bit later in the 1980s, first due to Shane and Yao, using a minimal hypersurface descent technique. It was proved that the standard torus does not support positive scalar curvature, at least up to dimension 7. A little bit later, Gromov and Lawson actually used a variation of this Dirac operator technique to also treat the case of the torus in all dimensions. And in between, there were also a few other examples which are quite interesting. Namely, it turns also out that certain exotic spheres in certain dimensions do not support positive scalar curvature. So this also tells you that this is somehow, at least for these kind of examples, this is kind of subtle, because the existence of this a metric with this curvature property depends on the differentiable structure in general. Now, from this point of view, it looks a little bit like the Dirac operator can treat everything. That's not quite true, because you can, in this realm, consider certain manifolds which are not spin, which means that this spin Dirac operator does not exist, and then this method does not apply anymore, but you can still prove using the minimal hypersurface descent that these manifolds do not support positive scalar curvature. And a particular example of that would be the 4 torus connected sum with complex projectives to space. But maybe let's focus on the Dirac setting for now and talk a little bit more about that. It is, however, quite mysterious at the moment still what the precise relation between these two techniques is. And one would ideally see some sort of method that can also treat this case, but this is not clear. But in the Dirac setting, one can actually treat all these examples in a uniform way. As I said, this comes out of the Dirac operator and index theory. So on a spin manifold, you have the spinor Dirac operator, which has a numerical invariant associated to it, the Fredholm index, which can actually be defined as the dimension of the kernel of some part of the operator minus the dimension of the kernel of some other part of the operator. And this can be computed using the Thier-Singer index theorem to be a topological invariant of the manifold, the so-called A hat genus. And the statement is that if this A hat genus is non-zero, then the manifold does not support positive scalar curvature. And this comes out of a certain kind of Weizenberg formula, which is in this setting usually called the Schrödinger-Lignerowicz formula. So it was first used by Lignerowicz, but it already appeared in a much earlier paper from the 1930s of Schrödinger, which tells you that d squared is, so the square of the Dirac operator is the connection Laplace operator, which crucially is a non-negative operator, plus the scalar curvature. And roughly speaking, what this means is if the scalar curvature is positive, then 0 cannot be in the spectrum of this Dirac operator, so it cannot have a kernel. And because the index is essentially defined in terms of the kernel, the index would have to be 0 if you have positive scalar curvature. So, and read in the other way, it means that if you have non-vanishing A hat, then you cannot have any metric of positive scalar curvature. And now this principle can be generalized simply by adding more algebraic sophistication to the index construction, in a sense. And the first improvement of this would be to get an invariant in the real K-theory of the point. And this essentially contains the same information as the A hat genus in dimensions which are a multiple of 4, but in dimensions 1 and 2 modulo 8, this contains another C mod 2 valued invariant, which can treat, for instance, these exotic spheres. And then this invariant is actually very good to treat simply connected manifolds. It actually in high dimensions tells you everything. But once you go beyond simply connected manifolds, this sort of a general principle in geometric topology, you have to take the fundamental group into account, and then you get an invariant which lives in the real K-theory of the group C-star algebra of the fundamental group. This is the so-called Rosenberg index. And this can, for instance, be used to treat the case of the torus and many other examples. And in fact, this invariant contains all the other two. So if we just want to look at index invariants, it's in a sense enough to look at this one. But now let's come back to the original question, namely metric inequalities, so or distance estimates. Let me recall again that in the case of a positive Ricci bound, we have a diameter bound. But in the case of a positive scalar bound, and I will usually now consider a lower bound of n times n minus 1, which is the lower bound, which is precisely the scalar curvature of the sphere, then you cannot have any diameter bounds because you can, for instance, take the sphere across the real line. But now I want to switch this up a little bit. In a sense, this example is too easy for this problem because you can just completely support the positive scalar curvature on this factor. And the question becomes much more interesting if you replace the sphere here by one of those manifolds which do not support positive scalar curvature in themselves. So these examples that we've discussed in the previous slides, of which we now know there are many. And maybe let's treat the case of the torus. So now we, in a sense, we know we cannot just do this obvious product construction. But we could imagine that, well, maybe the torus itself is not positively curved, but now when we add an additional direction, we can perhaps scale the metric on the torus in such a way that we get curvature in that direction. Yeah? And this is sort of the idea, this ansatz with a warped product. So you can try to find metrics on the torus times an interval just by doing this warped product construction, say, where you take any function phi, which is defined on an interval, and you rescale the flat metric on the torus in this way. And you want to achieve that the scalar curvature is equal to some constant, say. And this is, it then boils down to solving an ODE, because the scalar curvature on a warped product can be computed in terms of this ordinary differential expression, and you set that equal to n times n minus 1. And you can solve that explicitly. You get a solution, looks like this, cosine nx over 2, and to the power of 2 over n. What you notice is that, first of all, in dimension n equals to 2, this is really the warped product description of the standard sphere. Yeah? So n equals to 2 is this picture. You also notice that the solution collapses at the tips, so it becomes 0 at the tips. So it cannot continue it to be a non-degenerate metric beyond that. And however, in higher dimensions, this has nothing to do with the sphere. So it's both like topologically and metrically something completely different. Maybe a still misleading picture would be this one. But in a sense, the question now becomes, can you do any better? So now we looked at these warped product examples, and you might say, well, that's still a particular construction. It's not a fully general metric in this situation. And here we come sort of to the main question. That's actually a conjecture, which was, the ideas probably are older, but they were sort of repopularized in the 2018 article, Metric Inequalities with Scalar Curvature by Gromov, which started a lot of these developments. And essentially what Gromov predicts is that this warped product construction that I've shown you before, the previous slide, is the best that you can do in this situation. So more precisely, you look at a compact manifold which does not support a metric of positive scalar curvature, so for instance the torus, and you look at a Riemannian metric on this manifold times an interval. So you look at the cylinder over that manifold, look at the Riemannian metric on that one, a completely arbitrary one, except that you want to have a lower scalar curvature bound of n times n minus 1. And then the prediction is that the distance between the boundary components of the cylinder, and now you measure the distance intrinsically with respect to the metric G, where you have the scalar curvature bound, that is strictly bounded above by 2 pi over n. And this number 2 pi over n is precisely the number that we got in this explicit warped product construction that we've seen before. Okay, so what do we know about this conjecture? So Gromov in this article, he already showed it for the for the torus or some related manifolds, which are called enlargeable manifolds, using a variant of the minimal hypersurface descent technique. A little bit later, I showed that this conjecture holds true whenever the Rosenberg index is non-vanishing. That means this most general kind of index obstruction to positive scalar curvature. In particular, this includes also the cases where, let's say, the A hat genus is non-zero or the Hitchin alpha invariant is non-zero. So this already treats a lot of examples. For instance, it treats, due to a theorem of Stefan Stolz, all simply connected manifolds in high dimensions, in particular the exotic spheres. It treats the torus in all dimensions, or in more generally all enlargeable spin manifolds. And it also treats, for instance, so-called spherical manifolds, which are spin and satisfy the strong Novikov conjecture. This is because this sort of index invariant here can be related to the Baum-Kohn and Novikov assembly maps. Yet a little bit later, it was shown by Gromov and then also made more precise by Daniel Rede that this actually holds for all orientable manifolds up to dimension 7 at least, using a yet more sophisticated version of the minimal hypersurface technique. I want to highlight now next one more result which we got a little bit later, which is related to this and gives you a little bit more geometric feeling what is happening when you approach sort of this bound. And that also includes a rigidity result. So this is results of myself together with Simone Cecchini, where we're considering a more general Riemannian spin manifold, which has two boundary components. And you have a condition, a topological condition, namely that the hat genus of those boundaries is non-zero. And then you have a condition on the mean curvature at the boundary, which should be bounded below by some particular number, which is this tangent function here. And that tangent function is, in fact, the mean curvature of the slices in this warped product example that we've considered before. And this depends on a certain parameter L. And then the prediction is that the distance between the boundary components is bounded below by 2L, where L is the parameter that's in the tangent here. So maybe it's better to look at a picture here. So that's the situation. We have a spin manifold with two parts of the boundary. One I call delta minus, another delta plus. I have a lower bound on the scalar curvature in interior, and I have a boundary condition, namely that at all the boundaries, the mean curvature is bounded below by a negative number, which is this tangent. So negative for the mean curvature means for myself that the mean curvature vector points outwards, or in other words, if you push the boundary a little bit outwards, the volume will become smaller. So that will be the typical situation. And then the prediction is that you have this upper bound on the distance depending on this lower bound on the mean curvature here. And in fact, what we also know is that if we're in this situation and we have equality of the distances, we have rigidity. In a sense that if we have equality of the distances, then the manifold is already isometric to a warped product, and the warped product is precisely the same warped product as in the example that we've considered. And in fact, the cross-section in that case will have to be Ricci flat. In fact, it's a manifold that admits a parallel spinor. And as a corollary of this, we already known this before, but the corollary we get in particular that the width or the distance between the boundary components is strictly bounded above by 2 pi over n. That's just because this tangent function here tends to infinity if you L approaches pi over n. And this means that once you get close to the sort of critical distance, this hypothesis will essentially become vacuous. Or you could sort of read it the other way around and say if the distance becomes too large, then the mean curvature has to explode in a negative direction at some point, and the manifold has to collapse in a certain sense. Now, how is this proved? So the key proof idea is, so it's using the Dirac operator, and you're not just working with the Dirac operator itself, but the Dirac operator is modified with a scalar potential depending on some function, and the function itself depends on a distance function. So in a sense, you cook up some function which depends on the distance to one of those boundary components, say. And you then get a modified version of the Schrödinger-Lignerovich formula, which involves the usual term that we've seen before, and it involves some other terms which involve the function. And this essentially behaves in the same way as you would compute the scalar curvature on a warped product if this function f was essentially the mean curvature in the warped product. And then you can arrange things in such a way that if the distance is too large, you would get a positive lower bound here, and you would show invertibility of the operator, and then you use index theory to get an obstruction. And in the case of equality, you can analyze the situation a little bit more, and you will in the end get precise control on the Hessian of the function f, and thereby control on the Hessian of the distance function, and you will conclude that you have to be a warped product like this. So in a sense, in the end, it's the method in the end, after you've done all of this, is very similar to these classical comparison results for sectional curvature and Ricci curvature in the end, where you also want to study the Hessians and Laplacians of distance functions. Okay, so this is the rigidity result for distance estimates and scalar curvature under these hypotheses. Now, you can, in a sense, here we have sort of one distinguished distance, one direction, and we get an estimate on them. We get rigidity. It turns out this idea can in a sense be iterated if you have multiple directions. And let me mention a result which is due to Gromov and also due to Wang, Xi, and Yu, which takes this in a sense to the extreme, where you take as many distances as you have dimensions, and then in the end sort of only a point remains. And then in a sense you get an unconditional type of estimate which looks as follows. So you start with a Riemannian metric on the cube. This is an n-dimensional cube, and the scalar curvature should be bounded below by n times n minus 1, our favorite constant. And then the conclusion is that these quantity, which is the inverse of the square of certain distances, is bounded below by a certain particular constant. Now, what are these distances? So these distances are just the distances between opposite faces of the cube, but you measure them with respect to the Riemannian metric G that you're given. And you get this estimate, and in particular what you can conclude if you pass to the minimum of the distances and then to the inverse of that, you get that the minimum of the distances, the i's, has to be bounded by a certain constant again, which is just depending on the dimension. And this in a sense tells you that positive scalar curvature somehow prevents you from expanding in all directions simultaneously. It tells you that if you have positive scalar curvature, then somehow there must be, in a certain sense, one direction which is relatively small. And that can be, in fact, proved by iterating this idea of just adding multiple potentials to the, this idea of adding a potential to the Dirac operator. In a certain sense, you can iterate it by adding multiple potentials, and you'll obtain that result. Okay, now that was sort of the part on metric inequalities. Remember in the beginning I also had several results for stronger curvature conditions which were related to the structure of non-compact manifolds. Let me see what we can say here in the case of scalar curvature. In particular on the structure of manifolds of multiple n's and positive scalar curvature. So again, let us recall, positive Ricci curvature means that we are connected at infinity, so only one end. And scalar curvature allows more than one end, of course, because we can take the sphere across the real line and we have two ends. Gromov and Lawson, back then, when they showed that the torus does not support positive scalar curvature, they already showed results in that direction. Namely, they showed that the torus across the real line does not support a complete metric of positive scalar curvature. So even if you allow the scalar curvature to decay to zero at infinity, as long as it remains positive, in fact, as long as it is non-negative and positive somewhere, this is not possible on the torus across the real line. And in fact, we already know, we also know this holds whenever M is a spin manifold, where this index theory tells us that it does not support positive scalar curvature. Say if we know that the Rosenberg index or any of the other index invariants is non-zero. This, and the same is true then. This was in fact first observed by Rosenberg, but he, at this point, I think he only proved the case where a uniform lower scalar curvature bound is ruled out, and then Simone Cecchini and myself, we added the sort of additional parts to also remove the scalar curvature positive but decaying to zero, which is not possible in this case. And this, in a sense, leads to a conjecture which is, in a sense, parallel to Gromov's conjecture that I mentioned before, which was actually formulated earlier by Rosenberg and Stolz, which tells you that, or which predicts that if you have a compact manifold which does not support a metric of positive scalar curvature, then the manifold times the real line should not admit a metric of positive scalar curvature which is complete. And in particular, we already know this for whenever we have an index theoretic obstruction to positive scalar curvature on M. And now I'll come to some results which will be related to the variation of the minimal hypersurface techniques. The question is, can we say something here in a more general situation where we're not assuming an index theoretic obstruction to positive scalar curvature, say. And for that, let me introduce a concept or a notation, namely an open band is just a non-compact manifold which is supposed to be connected, and we have a decomposition of the space of ends into two Klopen subsets. So maybe that should be one possible picture. So we have this non-compact manifold which has any number of ends, and we just label the ends that we have, some of them by plus and the others by minus. In fact, you could have infinitely many ends. You could imagine this to be like some sort of tree structure where the space of ends is a counter set. This is all allowed as long as the decomposition of the space of ends has to be into two Klopen subsets. And now we get a relation to scalar curvature using hypersurfaces. So we'll have to talk about hypersurfaces in that situation. So a hypersurface is just a codimension 1 submanifold inside our open band. And what I'm actually interested in is separating hypersurfaces. That means hypersurfaces which separate this one chosen part of the boundary from the other part of the boundary. So this would be an example of a separating hypersurface, because if we want to go from this infinity to that infinity, you have to somehow pass through that hypersurface. But sort of for technical reasons, we do not want to have any like unnecessary components in our separating hypersurface. So in this example that I've drawn, this component of the hypersurface is kind of unnecessary to separate, because we can anyway go around here, and these two components would be enough to separate. So let's talk about properly separating hypersurfaces. That means a separating hypersurface such that if we remove any sort of components, it's not separating anymore. Okay, and then we have sort of a technical result which obtained together with Simone Cecchini and Daniel Rede, which tells us that in this situation, if we have an open band and we have a complete metric of positive scalar curvature, and we are in dimension up to 7 in order to apply minimal hypersurface methods, then there already exists a properly separating hypersurface which in itself admits positive scalar curvature. So in a sense, this could be said to restrict the topology of a manifold which has multiple ends and positive scalar curvature, because it tells you that you have to have hypersurfaces with positive scalar curvature in there. And the proof ingredient here, this is something which has been introduced by Gromov recently, which is a variant of the minimal hypersurface technique, where rather than making the mean curvature 0 or minimizing volume, you want to prescribe the mean curvature of the hypersurface to be a certain function. And this is in a sense completely parallel to this idea of adding a mean curvature potential to the Dirac operator. So it functions in the same way, and this has been popularized recently by Gromov, has been used by Xintian Zhu. It's also been very successfully used by Shodo Li to treat spherical manifolds in dimensions 4 and 5. It turns out that actually this existence result that we're using here is a special case of the existence of so-called marginally outer trapped surfaces in a certain situation, and which goes back to a result of Anderson, Eichmeier, and Metzger. That's just as a side remark that these ideas they have been around in a sense. Now, but why did we? I wrote here proposition, not theorem. The reason is that this was actually sort of a technical step towards answering a question that we had in mind more prominently. And the question is also something which was sort of vaguely asked by Gromov. In a sense, question is whenever, what are situations where a hypersurface which itself does not support positive scalar curvature already obstructs positive scalar curvature on the ambient manifold. In a sense, this is precisely the kind of situation that we want to look at here if we have this situation from before in mind, because this theorem or this proposition gives us existence of a hypersurface with positive scalar curvature, and if we had some sort of topological reasons that such hypersurface cannot exist, then we get a contradiction and we get a result. And the question is here, okay, when does it happen? So of course it's not asked like this, because you need to put some conditions, because you can always embed a small torus somewhere in any manifold. So the manifold or the submanifold should be sort of homotopically interesting, and one natural condition that you can put here is that it is essential or incompressible, which means that the inclusion on the fundamental groups is injective. And in that situation, we have a theorem which is based on this proposition. So the theorem is, if we have an orientable manifold, and we restrict here to dimension 6 and 7, and a compact two-sided hypersurface which is incompressible, meaning that, as I said, the inclusion induces an injective map on fundamental groups, and suppose that this hypersurface does not support positive scalar curvature. And then we have an additional topological condition, namely, this is related to spin structures, which says that either X and M are both almost spin meaning that the universal coverings are spin, or both of them are totally non-spin, meaning that universal coverings are not spin. So they have to behave in the same way with respect to the spin condition. And then we kind of answer this question and can conclude that X does not support a complete metric of positive scalar curvature. Now, sort of these conditions, this was not part of the original question, and you might ask, well, is it necessary? And if you know the sort of surgery theory of positive scalar curvature, then this will not be surprising to you that this is in fact necessary. So you can look at certain kinds of examples like this here. So it turns out that the K3 surface times the torus, if you connect this with something non-spin like CP2 times S2, then this will admit positive scalar curvature, but it contains K3 times S1 as an incompressible hypersurface, which is spin and does not support positive scalar curvature. And this result, forgot to mention here in particular as a corollary, gives you that this Rosenberg-Stolz conjecture holds up to dimension 7. This example and sort of this spin conditions here, they tell you that this is a little bit subtle. So the methods here, they are not related to the Dirac operator or spin at all, but you have to use the surgery theory of positive scalar curvature here, and then the spin condition somehow miraculously, or maybe less miraculously, depending on your point of view, comes back in, and you get these subtle counterexamples. And let me thank you for listening at this point.
Thank you very much. Are there questions?
Gromov-Witten invariance?
Not that I. What's the question precisely?
If you have the symplectic manifold, and you have the metric on it, and you have curvature bounds, do you get consequences for Fukaya category?
Can you repeat that?
Do you get consequences for the Fukaya category on a symplectic manifold if you have such metric curvature?
Not that I know of.
Okay.
I mean, in dimension 4, there are some Seiberg-Witten obstructions to positive scalar curvature, which sometimes use the presence of a symplectic structure, but that's sort of the only relation to that I'm aware of.
If there are no more questions, then thank you again. And I suggest that